For our last set of videos, as we introduce some of the basics of statistics, we're going to look at correlation and regression. So let's start with correlation. Correlation shows the relationship between two quantitative variables, and later on we're going to look at the relationship between two variables when they are ordinal. So there are different correlation methods depending on if you're interval or ratio. We'll use the Pearson product moment correlation coefficient for that, which is what we're going to show in this video. If we have ordinal data, so attitude scales, then we use what's called a Spearman rank correlation. So we'll get to that in a later video as we dive more into descriptive analytics. But first, let's continue our discussion introducing some of the basics of statistics. So correlation shows the relationship between those two quantitative variables. And as I said, we're using the Pearson product moment correlation coefficient, which looks at the relationship between two interval or ratio variables. Now, we've already looked at how to represent the relationship between two variables in creating, oh, maybe we haven't. Okay, let's look at it now just in case we haven't. Some of these videos I've made in various orders. So I have videos on scatter plots, but have I shown them to you yet? Maybe not. All right, so let's create a scatter plot or a scatter diagram that shows the relationship between two variables. So for example, let's suppose that we have a jeweler who's ran an advertisement in a local newspaper reporting the size and the price of diamonds. We can show the relationship between size and price of diamonds by creating a scatter plot. To create a scatter plot in Excel, we would take our data, so here we have size and price, and we can highlight our information, and then we can insert, and the one that is the dots here is a scatter plot. So let's create this scatter plot here. And we can, in our scatter plot, we can add labels to it. If you're on Windows, you can push the little plus here to add pieces. You can also do it up in the chart design ribbon where we add elements. So we can add a title to the horizontal axes, and we can add a title to the vertical axes. Okay. Now, since when I highlighted the data, I didn't highlight size and price, it didn't automatically do that. I can go in and change my data here to have a name. So I'm going to just remove this data and change it to this data. Was it smart enough to give me a name? Maybe not. I can add them in by hand. Let's try this again. All right, give me this. Insert scatter plot. Add titles. All right, well, be a jerk and I'll write them in by hand. All right, so the ones that are going from 0 to 2.5, that is going to be our size. And on our vertical, we have our price. If you are simply looking at the relationship between in terms of correlation, it doesn't actually matter which one you put on the vertical and which one you put on the horizontal. When we get to regression, where we are trying to predict one, then it does matter which one you put on the horizontal and which one you put on the vertical. So we want size here on the horizontal. If we say that size, it's what's going to determine the price. So first we're looking at correlation. So is there a relationship here in our data? When we are looking at these relationships, they don't necessarily indicate cause and effect. So we can have correlation without causation. So when we do our experimental design, as we talked about before, we are trying to get to causation. But we would create scatter plots and look at correlation, even if we're doing surveys and we ask two questions and we want to look at the relationship to the responses to those two questions. So correlation does not automatically create causation. Now, when we look at correlation, we're looking at the strength of the relationship. When you are looking at your scatter plot, if there is no relationship, then it's going to look like random scatter. If there is a relationship, we're going to see some kind of trend. So it's possible that you can see that as one increases, so as the size increases, the price might increase as well. And so here we have a positive relationship. So we can look at the direction of the relationship. If it is direct or positive, then that means that when one increases, the other increases. We could also have an inverse relationship or a negative correlation, which says that as one increases, so here, whatever A is, as A increases, if that makes B go down, we have an inverse or a negative correlation. Okay? So when you get your correlation number, if it is positive, we have a positive correlation. If it is negative, we have a negative correlation. And we also look at the size of the relationship, the strength of the relationship. A really, really strong relationship would look like this. In fact, this is a correlation of 1. That is, the amount of increase in A causes the same amount of increase in B, or is related to, not necessarily causes. But here we have a strong relationship. A weaker relationship is one that's going to look more like a bit more random scatter, but notice it still has that upward trend. So it is going to be a direct or positive correlation, but the more kind of scatter, that variability you have, the weaker it is. Now, if there's no relationship at all, it looks like that random scatter, but it also doesn't have any direction to it. So we look at the direction and we look at the strength as we are looking at our correlation. So we first get an idea of the amount of correlation by looking at our scatter plot, our graph that shows this. So already we can see here that we seem to have a direct relationship. So we expect that correlation measure to be positive, and we can see that it's probably going to be on the stronger side, just given the fact there's not a bunch of random scatter. It's all closer to that line that I drew there. So it looks like it's going to be on the stronger side. It's going to be more direct. So we're going to end up with a larger positive number as our measure of correlation. When it comes to your correlation coefficient, it's actually going to range between -1 and +1. If your correlation is equal to 0, then you have no relationship at all. If it is very strong and direct, it is a positive relationship, it's essentially a straight line, then it's going to be a +1. If it is a strong relationship but moves in the other direction, it's a -1. Okay? So you can see how the relationship is measured in terms of strength and in terms of direction. Okay. We're going to use the Pearson product moment correlation coefficient to measure that relationship. This Pearson product moment correlation coefficient describes a linear relationship, so we're only looking for straight lines here. And they have to be two quantitative variables, and in fact, not just quantitative, but they got to be ratio or interval. Okay. As I said, it ranges from -1 to +1. So if R is equal to 0.7, for example, if the correlation coefficient between education level and income is an R equals 0.7, then we have a strong relationship and a direct or positive relationship. When one variable increases, the other increases. So to tell the strength of the relationship, we compare it to 0. So the bigger the number is away from 0, the stronger the relationship, regardless of whether it's a negative or a positive. Now, to get the Pearson product moment correlation coefficient in Excel, make sure we have big enough here, we do equals Pearson. Okay, and then we will highlight our size, comma, and then highlight our price. Close parentheses. Here we get a Pearson product moment correlation coefficient of 0.95. So you can see that it's positive as we predicted, and you can see that it's actually really close to 1. Okay. The actual calculation from the correlation coefficient comes from this formula here, where what is on the top here is what is called the covariance. So we're looking here at not just the difference in the change in the X value, whatever's on the horizontal axes here, that being the size of the diamonds, but also we're looking at the variability in terms of the price of the diamonds. So when we're looking at correlation, it is going to be dependent on the standard deviation of our X's, so in this case our sizes of the diamonds, and our standard deviation of our Y's, our prices of our diamonds. So it's going to depend on the variability of both the diamond prices and the diamond sizes, but it's also going to depend on this relationship between, so when one changes, when we change size, what is the change in the price? And so we have this measure here on top of the formula, which looks at covariance. Okay. It is taking the deviation between size and the deviation between price and multiplying them, and that creates what is called a cross product. Right? So we could actually do this by hand if we really wanted to. We could find the average size and the average price and look at the size minus the average and square it. We could take the price minus the average price and square it. And we could also take the difference between the size and the average size and the price and the average size and multiply those differences. Then what we would do is take those, because we go back to our formula here, this is the sum of the cross products divided by our sample size. So we could take this column here of X minus X bar, Y minus Y bar, add it all up and divide by our sample size of 32. That would give us the top part of this formula. And the bottom part of the formula, that standard deviation calculation, we would find by summing up the differences squared. So we would take this X minus X bar squared column, total that up, divide by 32, and take the square root of that. And so if you wanted to go through that entire process, we could do that calculation by hand and come up with 0.95. But we're never going to do that by hand because Excel will do it. Any statistical software you want will do it for you with just a simple click or command line. So while this is the formula itself, you're never going to do that one by hand. Often what you're going to get is some kind of correlation matrix output. Okay. So while we're talking about output, correlation matrix output, let's actually look at this as well in Python. So just a reminder, if you want to work with us in Python, just put this down a bit, you can find the workbooks at drstephpowers.github.io/BIA, and we are currently working through some of the supplemental material. Right now we're working through correlation. So if you click on correlation, it will open up here in GitHub, open in Google Colab by pushing that button. What happens is that it opens a copy of this workbook in your Google Drive or using your Google Drive. If you log into your Google Drive, if you save a copy in your drive, you will then be able to run and edit this code. We are actually going to be using data like this diamond set that we've been showing. To access that diamond set, if you just go back to where we were, under data here on the left, we are working through the statistics number 3 here. Click on that, click download right here, download that Excel file, dump it into your Google Drive, and then in just a moment, we will link our workbook and our Google Drive. To do that linking, what you will do is you will import pandas as PD. This allows you to use a package to bring in the Excel files. And then from Google.Colab, import drive. So once I've saved a copy of my workbook, I can then link my workbook to my files by running this command line here. It will ask me about connecting to Google Drive. I'm going to pick one of my Google Drive accounts to do that. I give it permission. And what it is doing is linking my workbook to my Google Drive so that I can import files. And one of the files I'm going to be importing is statistics3.xls, and we're focusing here on the sheet name Diamond to get our data set. You will need to tell it where you have dropped that statistics3 file in your Google Drive. For me, it is inside a folder called BIBA Handbook and inside a folder inside that called Appendix. If you're dumping it straight into your Google Drive, no folder, then just remove these two that I have highlighted here. If you simply have it inside one folder, then replace both of these with just your folder's name. So I'm going to import my data set. Here we're just going to call the data set X. You can call it whatever you want. Well, almost anything. There are some words that are protected because they have special meaning to Python. Words like lambda, words like normal, that you'll want to stay away from. So if you get a weird error, then change the name. All right, so x.head is going to let us check on what we imported to make sure that it is what we think it is. So we are applying head to show us the first 5 rows to our data set that we called X. And so we can see here our sizes and our prices. To create a scatter plot in Python, we need a package called import matplotlib.pyplot as PLT. So we'll need to import that package. Then if you're going to create a scatter plot in Python, we're going to use that PLT package and tell it to plot. Whatever you want to be on the horizontal axes is going to be the first thing you list. So here from dataset X, we're going to take column called size space X. So just make sure that name matches whatever you imported it in. So here's the space, here's the parentheses. And then what goes next is we're pulling from dataset X the column called price space Y. Okay. Line styles equal none because at this point we just want the dots, and so we're going to say marker equals O to give us the little dots. You can tweak this scatter plot a lot. You can change the color of the dots, make them bigger, make them smaller. We can add labels. Here we're adding an X label saying size and a Y label saying price, and then saying please output the image doing plt.show. If you skip this plt.show, it'll still output your graph, but then it has a bunch of text on top of it, which is not very pretty. So just show us the graph is what we're saying here. So what we do is we get, just like you saw with Excel, here is our scatter plot. To do correlation and create a correlation matrix, you do need to take your original data set and reduce it down to just the variables that you want the correlation from. Because if I just do X, the original data set, and then I use the command core, and I use the method pearson, because remember later on we're going to talk about Spearman rank, so there are other methods. If I do that, it's going to add in diamond here as part of my correlation matrix. And that diamond was diamond number 1, diamond number 2, diamond number 3. So that column has no meaning. So instead of doing this, what I'm going to do here is create a second data set, which is going to take the X data set, 2 hard brackets, that's the key to remember, 2 hard brackets, and then which columns of data set X am I going to count as X2. So here I'm just going to take size and price, and I'm going to say that create a new data set for me called X2. So then X2.head, if I take a look at how it turned out, is just the 2 columns. So it removes that 3rd column that just had the number, the diamond number on it. Which means then if I do X2, so apply the correlation to dataset X2 and use method Pearson, when I do that, I get a new correlation matrix. The diagonal here is always going to be 1 because when you correlate something with itself, it's always going to be a perfect direct relationship because size and size are the same thing. So it's obviously they're always going to be equal and move together. So those are always going to be ones on this diagonal here. What we care about is the off diagonal. And you notice they're the same because whether you look at size and price or price and size, it's the same relationship. So we get a correlation here of 0.94655, just like here we got in Excel. So you can find correlation and create scatter plots in Excel. You can also do it in Python. Now, there are common errors in interpreting the correlation coefficient, so be careful about how you interpret it. It is incorrect to interpret R in direct proportion to its size. So it's incorrect to say that R is the percentage association between two variables. We can't say there's a 60% association. So it's not interpreted as a percentage. So just be careful about that. Just because it happens to go to 1 doesn't mean it's a percentage. We will look later at something called R squared. And that one we can interpret as a percentage. So we'll get to that as we get to regression. So if R is equal to 0.6, we can't say there's a 60% association between the variables. So just be careful about that. R measures strength of association, how greatly the variables move together, but it's not a percent. It's incorrect to say that variables that have an R equal 0.8 have twice the relationship of variables that have an R equal 0.4. Again, we're going to be looking at R squared later on to be able to do some comparison here, but we can't interpret 0.8 as twice the relationship as 0.4. If R is equal to 0.8, then 0.64 of the variation is accounted for. If R is equal to 0.4, then it's 0.4 squared, or 0.16 of the variation is what's accounted for. So it's the R squared that gives us that proportion, that percentage that allows us to compare. The correlation coefficient on its own, just R, doesn't give us that. So in fact, an R of 0.8 and an R of 0.4, an R of 0.8 is actually 4 times the relationship than a R of, so an R of 0.8 is 4 times that of an R of 0.4, okay? It's incorrect to say that increasing the correlation from 0.1 to 0.2 is the same as increasing the correlation from 0.7 to 0.8. So again, leave it to R squared, we'll get to that later. It's incorrect to interpret the correlation coefficient in terms of arbitrary descriptive labels. It's incorrect to infer causation. It doesn't mean we have one causing the other just because we have a relationship. There could be something else that is causing both of them. And so it is not that A is causing B if there's a correlation between A and B. Okay. The correlation coefficient only identifies linear relationships. So we're going to get into forecasting in later videos where the relationship between two variables might change. So if we think about, for example, that at, let's see, what's an example? Let's just think about time. Okay, so maybe over time, initially, we get lots of growth. And so there's this linear relationship going up. Maybe it's not even linear. Maybe it's an exponential. It goes, woo, real quick. And then you get to a certain point and that relationship then changes. Maybe it drops. So then you have a polynomial, or maybe it's not a linear relationship at all ever. It's just that it's continually increasing quite quickly, exponential growth. Or maybe it increases quickly and then flattens off, so it's more logarithmic. So there are other types of relationships besides linear. We will get to those when we get to forecasting in our diagnostic analytics videos. But with the Pearson product moment correlation coefficient, we're only looking at a linear relationship. That is, they move up together. When one moves up, the other one moves down, or there is no linear relationship. So it's quite possible there's a relationship, but it's just not linear. The Pearson product moment correlation coefficient won't detect that, or will detect a weak linear relationship because it's trying to flatten out what might be, say, a polynomial relationship. The other thing to note is that outliers can greatly affect the correlation coefficient. Okay. So if we look at some examples of which ones are correct or incorrect interpretations, can you identify what's wrong? The strength of associations between scores on attitudes toward disabled person scale and the amount of exposure to persons with disabilities is 0.56. So R will give us the strength of the association. But we can't do, say, what we see here in 0.4. The correlation between height and weight is 0.4. The correlation is twice as high as that as the other group, right? Got to do it squared in order to look at a comparison between. The correlation between reaction time and the number of automobile accidents is 0.2. 96% of the variance and frequency of accidents is unaccounted for. In order to find out the amount of variance that is accounted for, we would take the correlation of 0.2 and square that. Two. Yep. Squared is 0.04. So in fact, the statement here that 96% of the variance in the frequency of accidents is unaccounted for is correct, because we would use R squared to find the amount that is accounted for. We can conclude from the high correlation between level of motivation and the number of elected offices sought that office-seeking behavior is caused, at least in part, by motivation. So we can't do that because, again, correlation is not causation. Okay. From correlation, as we said before, you do get a measure of strength of the relationship as we compare it to 0, and you do get a measure of the direction. When you start trying to get into interpretations as to the percentage and trying to compare different correlations, we can't use correlation on its own. We have to go to R squared. We have to square the correlation. So just be careful about that interpretation. Now, we have been, maybe I'll stop the video here. In the next video, we'll do correlation hypothesis tests.